lamp is on. Its circle of light rests on the desk, warm and steady, softening the edges of the room. You can let your shoulders settle. Your breathing can stay as it is. We are not going anywhere tonight. We're staying right here, in this armchair, with one book open in front of us, and we'll read only what the pages can hold. Tonight's chapter sits near the edge of what we know. Its title, A Universe Inside a Black Hole, may sound grand. It invites big, sweeping images. But we won't follow those. Instead, we'll hold the chapter gently, like a proposal written in the margins, clear, careful, and easy to set down. As far as we can tell, mainstream cosmology does not treat this as literal fact. It's a frontier idea, and we'll label it that way from the very first line. So the rule tonight is simple. When the scale grows cosmic, when the language begins to drift out past the lamplight, we'll return to something close. The armchair beneath us, the page edge under a thumb, the quiet weight of the book in our hands. We'll keep the reading calm. We'll keep the metaphors inside this house, inside this book. No rushing, no dramatic exits, just careful words. Read slowly, with the light steady and low. Let's place one definition on the page edge, right beneath your thumb, so you can return to it if the language begins to blur. In our gravity book, the one written in the language of general relativity, there's a line called a horizon. It's not a wall you can see, not a surface you can touch. It's a boundary drawn by the shape of space-time itself, a line past which messages can't return to someone far away. Here is the careful sentence. In the classical view, a black hole horizon is a causal boundary. It separates events that can send signals outward from those that can't. If you're standing far from the black hole, holding your own lamp and waiting for news, the horizon is where no more news arrives. The geometry stops it. The signal might be sent, the pages might still turn, but the message doesn't make it back to where you are. This is our first anchor, and it's worth underlining. The horizon isn't a thing. It's a feature of how space and time connect around mass and energy. It's geometry, not material. And if we're going to keep reading without stumbling, we'll need to hold that distinction steady, like a bookmark that keeps one definition in place while the rest unfolds around it. Now we can settle a little deeper into the armchair and turn one more page. The next line is where the language starts to slip. When we say, inside a black hole, what do we really mean? And just as important, what do we need to avoid saying? You've probably heard the phrase, time stops at the horizon. It sounds clean, final, but that phrasing depends on how we label time in our equations. And those labels, our coordinates, aren't the same as the physical experience of someone falling inward. If you were watching from your distant reading desk, you'd see the light from that object grow faint, redder, slower. The print might appear to pause, but that's about what reaches you, not what's happening inside. In the geometry itself, in the frame of the object falling in, the story continues. The pages still turn. So let's reread that line and simplify it. From far away, signals can fade and slow. From inside, the narrative doesn't stop. It just becomes unreadable from here. That's the distinction to carry forward. A plain, steady statement about what can be sent, what can be received, and where geometry draws its lines. Let's step to the window for a moment and consider a different kind of limit. Cosmology, the study of the whole universe, has its own horizons. These aren't black hole horizons. They're observational boundaries, shaped by the fact that signals move at finite speed and the universe has a finite age. There's only so much time for light to reach us, only so many pages we can read directly. As far as we can tell, everything beyond a certain distance must be reconstructed. We piece it together from faint marks, from patterns in light that did arrive, from the structure left behind. We don't have a direct view of the first page. We have echoes, traces, inferences. It's enough to build a story, but it's not the same as reading it word for word. So tonight, when we talk about horizons, we mean two kinds of limits: the black hole's causal boundary and cosmology's observational edge. Both are shaped by geometry, both limit what we can read, and both remind us that even in a well-lit room, some pages remain just out of reach. We'll place a bookmark here, labeled "What We Can Observe," and keep it close as we read on. Now let's return to the lamp, where the light is clearest, and look at the comparison that gives this chapter its name. It's a match between two ways of describing scale. It goes like this. If you take the observable universe, estimate its total mass energy, and calculate the Schwarzschild radius for that amount, you get a number that, roughly, matches the size of the observable universe. That resemblance has led to what some call the universe as a black hole idea. The math lines up in a way that feels suggestive. Two lines in two different chapters echo each other. So the question follows, does that mean something? Is it evidence? Or just coincidence? Here's the careful answer. The resemblance is real, but it's not conclusive. One possibility is that it hints at a deeper link. Another is that it's a product of how we define our terms, how we draw boundaries and choose comparisons. We can hold both views, like a margin note that reads, "Resemblance does not equal identity." The comparison is worth reading, worth noting, but not enough on its own to settle the question. Let's pause at the desk corner, where a bookmark sits beside a pencil, and make room for clarity. When we compare a cosmic radius to a Schwarzschild radius, what exactly are we comparing? Which total mass energy? Which definition of universe? It turns out the strength of this coincidence depends on our definitions. Define the observable universe one way, and you get one number. Define it differently, and the match shifts. If we're careful about what mass energy means in a dynamic, expanding geometry, the comparison becomes more subtle. This isn't a problem. It's just what it means to read precisely. In any serious book, we need to understand the terms before we interpret the sentences. And here, the resemblance is interesting but flexible. Different framings push it closer to, or further from, significance. Let's write a footnote here. Depends on setup. And leave it visible as we turn the page. Let's return the page edge to your thumb and reread the core definition. A horizon, in general relativity, is defined by what signals can reach a distant observer. It's a boundary in space-time, a feature of causality, of what influences what and when, not a barrier of material, not a gate that swings shut, just a place where the geometry changes and outward paths no longer lead out. Let's read that definition one more time, the way we might read a sentence that carries real clarity. A horizon is a causal boundary. Beyond it, signals don't reach distant observers, at least not in classical general relativity. That's the sentence. That's our anchor. And the rest of tonight's reading rests on it. Now we come to a harder page, the one where the classical equations break down. In general relativity's view of a black hole, there's a point called a singularity. That's where the math fails, where the predictions give way. The symbols lose meaning. As far as we know, a singularity isn't a physical object. It's a marker. It shows where the current chapter, the classical gravity book, runs out of sentences. It marks the edge of what general relativity can describe. Beyond that, we expect a new chapter, quantum gravity. But that chapter is not yet finished. So when we see the word singularity, we won't treat it as the end. We'll treat it like a torn page symbol in the margin, a reminder that the book we're holding is incomplete, that nature may be using rules we haven't yet learned. We can rest our hands on the open book for a moment, acknowledge the gap, and then turn to the proposals that try to bridge it. Let's move to the shelf, where we keep labeled hypotheses, and take down the first one. This idea belongs to a group of models that suggest the singularity, the torn page, isn't the end. If some new physics prevents the geometry from reaching that unreadable point at extreme density, then the equations might turn a corner instead of ending. And on the other side of that corner, there could be an expanding region. This is one possibility. It's not established. It depends on assumptions about extreme conditions, assumptions we can't yet test. But the idea is simple. If space-time resists infinite collapse, then the inside of a black hole might continue beyond the singularity. It might connect to something like a new universe. We'll place this idea on a footnote shelf labeled Continuation. We can read it, consider it, but we won't move it to the main shelf, not until the missing pages are filled in and the checks are in place. Let's add a layer to this proposal. Keeping the lamp steady as we look closer, some continuation models describe interior regions that, under particular assumptions, can behave like self-contained cosmologies inside a horizon. They expand, they evolve, they follow their own internal clock, but they stay causally disconnected from the outside. This makes sense within those models, but clarity matters. These constructions rely on assumptions about physics under extreme curvature, and on how we match the interior with the exterior. Those assumptions remain untested. The math can be written, the pages can exist, but whether nature reads them, we don't yet know. We'll add a margin note here, model dependent, and keep it visible. This isn't settled cosmology. It's a well-formed idea, a hypothesis held gently, waiting for tests. Now we take down a second proposal from the shelf. This one shifts direction. It suggests that if we extend the gravity chapter to include something called torsion, a geometric feature tied to matter's spin, then things might change at high density. Instead of a singularity, there could be a repulsive effect that halts the folding inward and produces a bounce. In the Einstein-Cartan version of gravity, where torsion is allowed, the equations predict this bounce. The deeper the inward folding, the stronger the repulsion, until space-time expands again. This isn't standard cosmology. General relativity, as usually applied, leaves out torsion. But this extension is consistent, and it offers a way to turn the page instead of ending it. We'll leave a new rule margin note at the desk corner, beside the pencil. This is a speculative extension, a rewrite of the gravity chapter not yet confirmed by observation. It's elegant, worth reading, but it stays on the proposal shelf. Within that torsion framework, one proposal draws the line explicitly. It suggests that a black hole interior, in the presence of torsion, could bounce and begin to expand. From the outside, it stays a black hole. From the inside, it becomes a cosmos. This is one possibility, not a position endorsed by mainstream cosmology, just a model-based sketch of how inward folding and expansion could be linked, if the torsion idea holds. The geometry continues. The singularity is avoided. The interior evolves in ways that resemble our early universe. We can stay in the armchair and hold this idea gently. It's internally consistent. It offers a path. But it still waits for observational signs that could bring it to the main shelf. Let's place a bookmark, torsion model, and keep it nearby, knowing that tests are still ahead. Let's take down one more idea from the shelf. This one zooms out. It's not about one black hole and one interior cosmos. It's about many, a population across cosmic time. It asks, what if each black hole seeds a new universe, and each new universe inherits physics that vary slightly from its parent? That's cosmological natural selection, proposed by Smolin. It's a speculative evolutionary idea. If black holes can spawn offspring universes, and if the offspring vary slightly, then universes that form more black holes would become more common, not by design, not by intention, but because that's what the mechanism favors. One possibility. That's the label we'll use, with a footnote, if the mechanism exists. It's elegant and, in principle, testable, if we find a way to link the idea to observation. For now, it stays on the speculative shelf, clearly marked. Now let's gather what we've read and ask the question that decides where an idea belongs. What would count as a check? What kind of evidence could move a proposal from the footnotes to the main shelf? The challenge is testability. Many versions of the universe inside a black hole idea are difficult to distinguish from what we already observe. The interior, if it exists, is disconnected from us. We don't have a window that looks through. When proposed checks do exist, they tend to be indirect. Consistency arguments, subtle patterns, comparisons read through careful assumptions. They're not direct views. They're more like footnotes and cross-references, and they depend on premises still being examined. So the question isn't, do we believe this? It's, what would make us believe it? For now, the answer is, we need more pages. We need the quantum gravity chapter. We need better tools for probing the early universe. And we need clear predictions that allow for solid tests. Let's reread that thought at the desk corner, where the bookmark and pencil sit side by side, and note that this, right here, is the frontier. Not a lack of ideas, a lack of decisive checks. Let's return to the shelf and check our labels. On the main shelf, solid ground, horizons as causal boundaries defined by geometry, space-time as shape, not substance. and the recognition that classical equations fail at high curvatures where we expect quantum gravity to begin. On the speculative shelf, the proposals. Continuation models that smooth out the singularity, torsion-based bounces, cosmological natural selection. These are model-dependent, based on assumptions not yet confirmed, and we label them clearly, like spines on books still being drafted. The line between shelves isn't sharp. It's not hostile, just careful. We can read from both, appreciate both. But we don't mistake footnotes for text, and we don't promote an idea until the evidence arrives. The lamplight is still steady. Your hands rest on the closed cover. We've read what this chapter can offer, marked the pages where the reading turns speculative, noticed where the story is still unfolding. We end with what's established. The horizon is a boundary drawn by geometry. The singularity is a marker of theory's limit. The continuation, bounce, and selection ideas remain as one possibility, clearly separate from the main text. The bookmark is in place. The cover rests, and the room around you is as calm as when we began. You can let your breathing stay easy. Let the warmth of the lamp soften the edges of the night. And when you're ready, let the book rest, knowing that the frontier is still being written, and we've read it with care, with clarity, with gentleness that keeps a reading safe. We opened this chapter knowing it sat near the edge of certainty, and we close it the same way. The idea that our universe might live inside a black hole is a frontier hypothesis, coherent within some models, untested in the ways that matter, and clearly labeled so we don't mistake speculation for settled fact. The horizons are real, the geometry holds, and the proposals that reach beyond classical limits are worth reading, as long as we keep them on the right shelf, waiting for the kind of evidence that could bring them forward. Bookmark for next time. We'll keep exploring the frontiers where observation meets theory, with the same care and the same clarity.